Okay, can I start? Are we okay? Okay. So I'm going to talk about SNISC. This is Succinct Non-Interactive Secure Computation. You don't hear me again? Okay. So this is a joint work with Rafael and Andrew. And as I said, it's called SNISC. SNISC, yeah, it's very hard to say, but okay. So let me tell you about the communication complexity of malicious multi-party computation protocols. My slides are moving super fast. Okay. Okay, so what are the lower bounds that we know for the round complexity? So if we assume a common random string, then we know that we can do it in 2 rounds. We cannot have non-interactive solutions, one-round solutions, because of residual attacks. Okay, so basically you can think of the following scenario. Let's say we are a set of malicious parties, and the honest parties are sending us their messages if it was only a one-round protocol. So if they send us the messages, then we can go offline, and we can try and compute the function based on the different inputs that we have. So we can keep using different inputs for ourselves, keeping the inputs of the honest parties the same. So we do this residual attack to find the inputs of the other parties. So one round is not possible for secure multi-party computation. And this is shown by Halevi, Lindell, and Benny Pincus actually. Okay, so if we don't have CRS, then their impossibility results, and the lower bound is 4 rounds. So we cannot do better than 4 rounds. And in general, actually, there are many protocols that they tried to achieve optimal round complexity. I'm not going to list all of them, but we do have optimal round protocols now. And if you know me well, you will know that I was obsessed with round complexity. So now I'm obsessed with communication complexity. So now that we have optimal round protocols, so now let's reduce the size of the messages in these rounds. Okay, so let's see what we know about communication complexity. So all the protocols that we know that they are optimal rounds and they are malicious, the communication complexity of all the protocols grows with the size of the function that we are computing. Okay, and here we want to reduce the communication complexity to make it independent of the function that we are computing. Okay, so we really want to squeeze the communication complexity. And there are some solutions based on I/O and using garbled circuits and garbled RAM, but they were not malicious and they were not based also on standard assumptions. Okay, so we don't know optimal round malicious protocols where the communication complexity is independent of the function that we are computing. And let's go back to the basics. So this was for multi-party computation, okay? But even for 2-party computation, let's just go back to the basics, okay? Let's look what's the situation only for 2 parties, okay? So, and let's go back to the setting of non-interactive secure computation. So actually, maybe the name here is misleading. So this is a 2-round protocol. So actually, I don't know why my slides are moving fast. So yeah. Yes. So actually, this notion was first introduced by actually Yuval, Eyal, Rafi, Manoj, and Amit. Okay, and it was also implicitly implied in Jetru's work. So there, what you're doing, so it's a 2-message protocol where we have the receiver and the sender. So the receiver sends the first message, and then the sender sends the second message, and only the receiver receives the output, okay? So the sender doesn't receive the output. As I said, we're going back to the basics. So only the receiver is getting the output. So this is the non-interactive secure computation. And I guess you know that the goal is that we need correctness, and we also want the receiver to receive just the output and nothing else should be leaked. Let me try to see what's going on, and it moves fast. Okay. And here we want malicious security, okay? So either the receiver is malicious or the sender is malicious. We want security against malicious adversaries. So let's see what's the state of the art. So for malicious non-interactive secure computation, we have the work of Yuval et al. And there's also another work by, I think, Payman, Benny, Pincus, Ben Riva. Who's the first one? Okay. Okay. This A person. Okay, so Yuval, they optimized the protocol. They did it based on OT. And then also Benny, they also try to do malicious security as well, based on cut and choose. Okay, so the protocols are incomparable. They're efficient in different terms. And then this is when you have a common random string. So if you don't have a common random string, in fact, we don't know how to do this non-interactive secure computation. If we use polynomial time simulation, it's impossible. Okay. But if we relax our security definition, and if we have super polynomial simulation, which was introduced by Rafael Paz, actually Manoj and Amit, so then we can achieve actually a non-interactive secure computation protocol. This is a work by Sai Krishna, Sanjam Yuval, Amit, and Akshay. Okay, so what is this super polynomial simulation? So it's again simulation-based security, but we allow the simulator to run in super polynomial time instead of polynomial time. And in this case, it's going to be quasi-polynomial time. Okay, and again, as I said before, it's impossible to achieve this with polynomial time simulation. We cannot achieve non-interactive secure computation without CRS with polynomial time assumptions. Okay, so here we have these protocols. Let's see about succinctness. Okay, so as I said before, yeah. I think there was one work based on IO, but I think it was only 3 rounds. Yeah.
2 rounds only, this is the only way.
You can use some other things. I think angel-based security and this kind of stuff. I think you can also use some other things. But yeah, like also angel-based in some scenarios is equivalent to SPS. So I would say SPS. Okay, so what about succinctness? Okay, remember what's the succinctness? So we want the communication complexity to be independent of the function that we are computing. And it can depend on the inputs of the 2 parties. Okay? And actually I also model the function as a Turing machine, just to be clear. So here we don't know. Actually we don't have anything. So we don't know of any malicious protocol which is succinct in the succinctness that I just defined. Okay? So in this work, we are actually building this succinct non-interactive secure computation protocols, what we call SNISC. So based on sub-exponential secure LWE, we can get malicious SNISC with super polynomial simulation and without CRS. And then also in the CRS model, based on LWE, we can also get malicious SNISC. Okay? So these are the results that we achieve. So before I go to the results, I'm going to show you the very easy protocol of getting semi-honest non-interactive secure computation from full homomorphic encryption. Of course, you know what's full homomorphic encryption. In general, we have like the encryptions of 2 values, A and B, and then we can actually evaluate homomorphically on them and get a ciphertext of the evaluated function. Okay, and then we can decrypt. So now this protocol is as follows. Also, Yuval mentioned this protocol yesterday. So I'm not gonna like stay too much on this slide. So let's see how the protocol works. So in the first round, the receiver encrypts here input X and sends an encryption of X to the sender. Then the sender homomorphically evaluates on the encryption of X and on his input Y, and then sends back the answer to the receiver. Okay, that's super simple protocol, and then the receiver can decrypt and find the answer. Okay. So here, let's see how we can make this protocol malicious. Okay, so if we use snarks, there's a way that can work if you use snarks. There's some complications, but we don't want to use exotic assumptions. So you know snarks is based on these exotic extractability assumptions, so we don't want to use snarks. I'm not going to say snarks again in this talk. Okay, no snarks. Okay, no snarks. Okay, so let's use zero knowledge, okay, plain zero knowledge, based on standard assumptions. Either like non-interactive zero knowledge or 2-round SPS zero knowledge, just use zero knowledge based on standard assumptions. So if we do that, then we will need to prove, let's say, the correctness of the FHC here, right? So if we put zero knowledge to prove the correctness of this, the size of the zero knowledge will depend on the size of the function, right? It's on the running time of the function. So we don't achieve the communication complexity which is independent of the function. Okay? So we cannot use zero knowledge proofs to prove the correctness of this protocol. Okay, is this clear before I go? Okay. Okay, so we cannot use plain zero knowledge because the communication complexity will still grow with the size of the function. Okay? No zero knowledge. The malicious adversary won. Okay? So let's see how we can actually win the malicious adversary. So the tools that we're going to use is fully homomorphic encryption. So we are based on fully homomorphic encryption. And here I want to say a huge disclaimer: this is not efficient. Don't try this at home. Okay? So this is a feasibility result, and then once we have the feasibility result, we can try to see how to make it practical. So don't try this at home. It's a feasibility result, and here we're in the theory of MPC, not the practice of MPC. Okay? Then we're going to use a delegation scheme. I'm going to define delegation schemes in the next slide. And we're also going to use actually a non-succinct, non-interactive secure computation protocol. Okay? And you will see how all these three tools will play together. So let's define the delegation. So with delegation, actually we would like to outsource our computation to the cloud or to somebody else. Let's say we don't have a lot of power. Yuval yesterday said that he's outsourcing his emails to the cloud. Maybe that's why you answer so fast. So let's say that we send our data to the cloud, and then the cloud is computing the function f that we want to compute and sends back the answer to us, okay? But the cloud can be malicious, so we need to verify that he computed the right function for us, okay? So for that, he's supposed to send a proof for the correctness of the evaluation. And then we receive the proof, and we are trying to see if the proof is correct, whether we can accept or reject. Okay? And what are the requirements here? So verifying should be much easier than computing. That's why we are outsourcing the computation. Okay? So if verifying takes a lot of time, then we should just not outsource the computation. So the verification should be very short. Here I have that it should be proportional to the size of the input, and I'm hiding logarithmic terms, polylogarithmic terms on the evaluation time of the function. Okay, and proving should also not take longer than evaluating the function. We don't want the cloud to keep computing forever. Okay, so the computation time should be only proportional to the running time of the function that we are computing. This TF that I have here. Okay, so this is delegation. And we can also have delegation where the input of the user is also private. Okay? So think very abstractively now that we can use, for example, fully homomorphic encryption. So basically what the user can do, he can encrypt his input, send it to the cloud, then the cloud can compute homomorphically on the encryption of the user, and get back the encrypted answer and also the proof that verifies the correctness. Okay? So here the function f that the cloud is computing is the evaluated function of the fully homomorphic encryption, okay? Because we're operating on ciphertexts. So this is the function of the delegation scheme. Okay, so it is possible to add input to this. I'm hiding some details here on how you can achieve this, but for now, just assume that this is possible. And here, I want to say that there's a work from Brakersky and Kalai. So they are adding privacy to the server. Okay? So they're not hiding the input of the user, they're hiding the input of the server. And also, they achieve witness indistinguishability. They don't achieve simulation-based security. Okay? So that's a step towards achieving security for both parties, but they only achieve security for the server. So we want to do this non-interactive secure computation, so it will be any input y. So the goal here is that we added input for the user, so now we also want to add input to the cloud. Okay? In our case, it won't be the cloud, it will be another user, right? So if we had delegation where both parties can have private inputs, then basically this is like non-interactive secure computation. Okay? And this is what we will try to do here. So let me try this in a little bit more detail, this protocol. And then we will try to go slowly to see how we can make this protocol to have inputs for both parties and also be malicious for both parties. So here I'm writing things slightly more formally. So the receiver in the first step generates the keys of the fully homomorphic encryption, okay? keys PK and SK, and encrypts her input X with some randomness Rx, and also generates, actually this is the first message of the delegation protocol. So in the first message of the delegation protocol, we need to generate also some public information and some secret information. Okay, so I call them here again public key and secret key. So these are the steps that the receiver does and sends to the center the public keys and the ciphertext. Okay, then the center can homomorphically evaluate. Okay, but we do this through the delegation scheme. Okay, so we're going to define the function that we want for the delegation scheme. It's going to be this function g. So as I said also before, our function g is going to compute the FHE evaluation of the two ciphertexts, right? So this is how we define g. It's the FHE evaluation. And this is the function that our delegation is going to have. So this is the second message of the delegation. It receives as input the public key, the function that we outsource, which is g here, and the two ciphertexts, and it generates the proof and the output ciphertext. Okay. So this is the second message of the delegation, and then the center sends the proof, the ciphertext, and also it needs to send the ciphertext on his input because the receiver needs to verify. Okay, so this is like the message of the verification. So to verify, you need the whole statement. So part of the statement is the ciphertext y. Okay, so you need to send all these three things. So first of all, and then you decrypt. Okay, so if you verify and if the verification was correct, then you can use your secret key and decrypt and get the right answer. Okay. So one thing here about the function of the delegation, which is the FHE evaluation. Most delegation schemes require this function to be defined at the beginning of the protocol. So when you generate the first message of the delegation, which is this one, you really need to know the function that you need to compute. And in our case, this function is actually a function of the input y of the center. So somehow we need the function of the delegation to be defined only in the second round, not in the first round. But we have a delegation scheme that achieves this property. And you can think that this is like an adaptive property because you need to define your function later. So it's called adaptive delegation. And this is a work from Brakerski, Holmgren, and Kalai. So we can get this property. So we can have a delegation scheme where the function is decided in the second round. And another thing that I hinted before, I said that we need to send the ciphertext y to the receiver. Okay. So if you notice, this is completely wrong, right? Because if I send the ciphertext to the receiver can decrypt and find the input of the center, right? So if I send this in the clear, I have the secret key. I can decrypt this, so there's no security here. So that was completely wrong. So we cannot do this. We cannot send the proof and the statement in the clear to the receiver. Okay, is this clear? Do you have any question? Okay. So we need to hide the proof and the statement. So how are we going to do that? Okay, so let's use secure computation. So let's use the generic secure computation to hide them. But here we're trying to build non-interactive secure computation. Now we want to use secure multi-party computation to hide the proof. Okay, so this is like conflicting. However, let's look at the sizes. Okay, so if we use a non-interactive secure protocol to actually hide these messages, this means that this protocol should actually, the function that you're computing with this protocol is the verification function of the delegation scheme, and this is succinct. So the verification of the delegation function is succinct. So it's okay to use a non-succinct non-interactive secure computation protocol to hide the proof and the ciphertext. Okay, so let's see how we can do this. So again, let's go step by step. So we're doing the same steps. We're generating the keys and the ciphertext. And now we are using this, let's call it inner non-interactive secure computation protocol, which is not succinct, okay? And remember we saw in the first slide that we know how to construct non-succinct non-interactive secure computation. Okay, so in the first message, we're actually running the first message of this inner non-interactive secure computation protocol. And now we are sending again the public key, the ciphertext, and the message of this non-interactive secure computation. Okay, So now the center computes the ciphertext and runs the second message of the delegation. But now this new inner protocol, the functionality that is going to compute is the functionality of the verification of the delegation. So if you see here the inputs that I put in this protocol, they are the same inputs that the verification algorithm takes as input. So all the inputs that we were supposed to input in the verification algorithm, because now our inner protocol computes the verification function, they are now all inputs to the second message of this inner non-interactive secret computation. Okay? Actually here it should be the public key. Not this. Yeah, this is wrong. This should be public key. Okay? And now we are sending the output, which is the encrypted output, and the message of the inner non-interactive secure computation protocol. Okay? And now, since this non-interactive inner protocol verifies the delegation, so the output will be either a 1 or bot, right? So if the message is bot, is not bot actually, we can decrypt and get the answer. Okay? So is this clear? And let's see why it is succinct now, okay? So let's see the communication here. So here all these messages are short, none of them depends on the function that we are computing. And here, MSG2 is actually short because this inner non-interactive secure computation computes the verification of the delegation, which is short. So MSG2 doesn't grow with the size of the function that we are computing. So here our communication complexity is indeed independent of the running time of the function that we are computing. Okay? So do you have any question? Because if you don't get this, you're not going to get the rest. Yeah. Yeah, so we're going to see later what properties we need from the FAT to get these properties. Yes. You're going to see in the next slides. To answer now, we need some perfect correctness, but you will see. Okay, any other question? It's clear? Huh? Yeah, it works. You want me to use it? Okay. Okay. Here I highlighted the differences from the previous protocol, but it's okay. So I show you this protocol, but it's not malicious. So we need to work slightly to get malicious security. So first of all, there's some malleability issues. So what do I mean by malleability issues? So when the sender gets the ciphertext X of the receiver, he can actually mull with it. For example, he can generate his ciphertext as a ciphertext depending on the input X of the other party. For example, it can encrypt X plus 1, okay? So because this is fully homomorphic encryption, you can generate an encryption of a 1 and add it to the ciphertext of X and get the ciphertext of X plus 1, okay? So nobody, there's no guarantee that the sender cannot do that. He can perfectly do that, okay? So this is this malleability issue that we can have here. And to get rid of this malleability issue, we actually need to have some way to extract the input Y of the center, okay? Because if we change the input of the center to be like correlated with the input X, then when we simulate, we'll have an issue. So we really need to extract the input Y of the center. And here in this protocol that I'm showing you, there's no way to extract Y. So we're just generating a ciphertext of Y, so we cannot really extract from here. So we need to add some extractability property to our protocol. So what we're going to do, we're going to use a malicious inner non-interactive secure computation protocol, okay? So if the protocol is malicious, then we can extract the inputs to this protocol. So what we're going to do, so in these two messages of this inner non-interactive secure computation, we're going to add also as input the inputs of the two parties, okay? So here we're adding the X and Rx, the randomness that was used to generate the ciphertext, and here we're adding Y and Ry, okay? So adding this, it proves that the ciphertexts are honestly generated. So now the center cannot do this mulling attack. He won't be able to generate this encryption of X plus 1, for example, okay? because we're adding this check, and our verification protocol, actually this inner non-interactive secure computation protocol, it checks the verification of the delegation, and also we're going to add 2 checks to check the correctness of the ciphertext. Okay. So we are checking this ciphertext. So this, what it guarantees that the randomness is consistent. So the randomness that you're using in these 2 ciphertexts, it guarantees that it is consistent. Okay, but it can be bad randomness. It is consistent, but it can still be bad randomness. Okay, and when we want to simulate, if the randomness is bad, this is very bad, and we cannot simulate. Okay, so adding these checks here in the non-interactive secure computation protocol, the inner one, checking that the ciphertexts are correct, sure, they're consistent under some randomness, but we need to accommodate bad randomness. So how are we going to solve this problem? Actually, we're going to use the perfect correctness of the fully homomorphic encryption scheme. So now if we have perfect correctness of the fully homomorphic encryption scheme, we can guarantee that the randomness that is being used is a good randomness. Because now when we are going to decrypt, the perfect correctness is going to guarantee that we are going to actually decrypt the right thing. So using perfect correctness, we can use good randomness. And another way of doing this, for example, could have been to run some coin flipping protocol to generate a good randomness, but we won't be able to do a coin flipping in 2 rounds, okay? So you can see the power of perfect correctness allows us to accommodate this attack on bad randomness. Okay? Yeah. Yes, I forgot it. Yeah. So here we also need as input MSG1. Yes, good point. Okay. So do you have any questions so far about the protocol? Okay. There's still another issue, okay? So here, the receiver can actually do some more attacks. For example, what it can do, it can actually generate bad keys, bad secret keys and public keys. And it can also generate bad keys for the delegation protocol. I think he can perfectly do that. And here, what's the deal? So if he does a bad computation here, a malicious computation, then if the computation is bad, he shouldn't get any message. Okay? So somehow we need to verify that he did this computation correctly before we generate the second message of the protocol. We could use some 1 round 0 knowledge, but we don't have 1 round 0 knowledge. Okay? This message is succinct, so we could use 0 knowledge, but we cannot use 1 round 0 knowledge because it's impossible. Also in the SPS model, it's impossible. Okay, so we need some form of witness encryption or conditional disclosure of secrets to do that. So just for those of you that you don't know what's witness encryption, but I assume most of you know, I'll go very quickly over it. So with witness encryption, we encrypt with respect to some language and some statement. So let's say a user has some input M, then she's encrypting based on some statement X of this language. And then even if she goes offline, the message is still there, and then a user can decrypt and find this message only if it knows a valid witness to the statement. Okay? And then if he knows the valid witness, it can decrypt and get the message. Okay? And what's the security here? So even if the statement is false or bogus, you still have semantic security, so you still cannot distinguish what you're encrypting here, so security is preserved. So if we use this, this is like a 1 round protocol. So we could add this check in the first round of our protocol to check if the public keys and the secret keys are honestly generated. However, we don't know how to do this witness encryption from standard assumptions. Okay? So we're going to use a 2 round witness encryption, sort of, which is like basically conditional disclosure of secrets. And usually how we achieve these primitives, we are using generic MPC, actually here 2PC. And since we are anyway using this inner non-interactive secure computation, we can also use the same non-interactive secure computation to check for the validity of the secret keys. Okay? So what we're going to do, so we are going to have this inner non-interactive secure computation to also check the validity of these messages, and only if these messages are correct, we are going to move to the check of the verification of the delegation. Okay, so we are adding more checks to this inner non-interactive secure computation protocol. Okay, and to be able to add these checks, we need to add now the randomness that we used for generating the keys. Okay, so in the first message, we are adding all the randomness that we used, and also here we need to add the public keys that we received from the receiver to be able to verify that these two are consistent. Okay. And now another thing that we can do, since we are adding everything inside the non-interactive zero knowledge protocol, and the non-interactive zero knowledge protocol actually it has the randomness, right, that we use to generate the public and the secret key. These are FHE, so it can actually also decrypt because it gets them as input. So we don't need anymore to send the ciphertext of the output outside. So we can have it inside. We can have this inner non-interactive protocol to decrypt inside. So let's enumerate all the checks that this inner non-interactive protocol does. So first it checks that the public keys are correct. Then, if you remember, it needs to check that the ciphertext of X and the ciphertext of Y are consistent. And also importantly that the receiver sent the ciphertext that it sent to the center is the same one that comes from his input, so he's using the consistent input across the whole protocol. And the other check is the check of the verification of the delegation. And if everything passes, it decrypts the ciphertext ST out to give out the answer. Okay. So now, if this MSG2 is not bought, we are getting directly f of x, y. We are getting directly the output. Okay. So do you have any questions about this protocol? Okay. Do you think we solved all the problems? Okay. Another issue is that we actually also need perfect correctness of the delegation scheme. So now, because we are also checking the correctness of the first round of the delegation protocol, so still we are actually checking that the randomness is actually not good randomness, consistent, but still the receiver can pick bad randomness. But if the delegation has perfect completeness, then we can still actually guarantee that even when we actually get the answer back, if the proof is accepting, we're going to be able to simulate perfectly. Okay, so we also need perfect correctness, completeness of the delegation scheme. Okay, so we are getting close to the solution, but there's one more issue, or maybe there are more. So there's something else that is happening here. So we have what is called spooky interactions. So what are the spooky interactions? So when the center is malicious, okay, what do we need to do to simulate the receiver? Actually, we will need to actually simulate the ciphertext X without knowing X. Okay, this is standard. So when you simulate the honest party, you need to have these hybrids where you are removing the inputs of the honest parties. Okay, so in this case, let's just focus only on the ciphertext X. So here we really need to simulate this ciphertext when the center is malicious without knowing X. Okay, so we have to do that. But here, there's this property that this inner non-interactive secure protocol has all the randomness that we use to generate this encryption. Okay, it has the randomness of Rx and the randomness of the RFHC. Okay. And remember, it was important to include them here because we wanted to be able to extract and verify that the public keys are correct. So it's very important that these go inside the functionality. So now, as I said before, we need to simulate without knowing X, but our functionality of the inner non-interactive protocol can actually decrypt that, okay, and can know what's X. So this is it's not possible. And this is actually something that happens also in constructions of delegation schemes. So there's some construction of delegation schemes that they are based on full homomorphic encryption, and they have exactly the same issues. And they are solving them using some other ways, which I have no time to tell you. But I'm going to tell you here how we are able to avoid these spooky interactions. So basically, we're going to use again the efficiency perfect correctness. So let's recall again. So now if we have the spooky interactions, what does it mean? It means the following. So the malicious center, even without knowing what is X, right? It can influence the result that the receiver is going to output in some undesirable ways based on X. Without knowing what is X and without being able to decrypt, he would be able to influence that. So now when we want to simulate the receiver, that is going to be a problem. But what we're going to do, we're going to generate a hybrid where we don't need this randomness R, del, and R FAT, okay? So in the very high level, I'm gonna describe this. So what is the setting? So we want to simulate the receiver against the malicious center. So when we're doing that in a hybrid, since the receiver is honest, the ciphertext and the public keys, we can assume that they're honestly generated. So we don't need to check them. So I can generate a hybrid functionality where I don't need to check the ciphertexts, okay? And moreover, another thing that I have to do, so when we are actually decrypting from the inner protocol, if the proof is accepting, okay, then I don't really need to have my inner protocol to decrypt if I have soundness of the delegation scheme. Okay, so I will not have to do that. So I can have a hybrid functionality for the inner non-interactive protocol where I don't need to check both the correctness of the ciphertext and the public keys, and at the same time I will also need to decrypt. So now I can create this hybrid that is completely independent of the randomness that we use for the ciphertext, which means that I can simulate, okay? So in that way, we can avoid these spooky interactions that I called before. Again, based on the soundness of the delegation scheme and the perfect correctness of the FHC. Okay? So that was at the high level the protocol. And there's no other problem. So we killed the malicious adversary. So let's see now all the properties that we need from our tools. So we need the FHC with perfect correctness. Delegation scheme also with perfect correctness, and remember it also has to be adaptive, that the function is decided in the second round. And we also need a malicious non-succinct non-interactive secure computation protocol. Okay? So I gave you the high level. There's some more technical details, but I don't have the time to tell you all the single details, but I hope you get the sense of it. So from all these tools we're getting this malicious this would be succinct. Yes, malicious succinct non-interactive secure computation. Yeah, when you're sleepy, that's what happens. So to conclude, so going back to this non-interactive secure computation, so we do know protocols that they use CRS or no CRS, and here we constructed malicious succinct non-interactive secure protocols for both the CRS model and the no CRS model, and everything is based on LWE. Okay, so here we can have sub-exponential LWE, and here just LWE. And as an open problem, so using this technique of using this non-succinct protocol to create a succinct protocol, we can look at this primitive. So there's this orthogonal setting of laconic oblivious transfer, laconic function evaluation, laconic conditional disclosure of secrets. And they try to do malicious security. So the laconic OT and the laconic function evaluation, they use snarks. And also the setting here, as I said before, it's orthogonal, because they're trying actually to make succinct one of the two inputs of the two parties. So they're trying to make the communication complexity independent of the inputs of one of the two parties. So it's an orthogonal setting. And in the laconic conditional disclosure of secrets, they tried to also build non-interactive succinct computation with malicious security, but the communication complexity there, it grows with the depth of the evaluated circuit. So we can use techniques from our work to see if we can actually do malicious laconic CDS as well. Okay? And with that, I will end the talk.
Questions?
everybody knows how to defeat the adversary.
Yes, yeah, your slides are really, really outstanding. Okay, so thanks for ending the talk.